Ladies and gentlemen, Crawford Griffith.
Hi. Okay, I am here to talk about MicroCore Labs emulators and how they work and how to build one. My name is Crawford Griffith again, and my VCF forum ID is Crawford. So this is basically what we're going to cover, who I am, which is not interesting, but who Ted Fried is interesting, and what MicroCore Labs is something that I've been working with, and I think it's applicable to vintage computing, and a lot of cool things can be done with these. Talk about plug-in emulators, kind of how they're different from totally virtual emulators, etc. Do a detailed design review of the hardware and software, and then some build information if any of you want to build one. Or I had some of my spare boards and I made some kits, and they were in the consignment area. So if you want a little bit more information on how to get started. I do have a success story with a vintage computer using these for debugging. So I want to talk about that. And then kind of at the end, some blue sky stuff, ideas of what can be done to further extend it and do other stuff with it. And then more info, some contact, and thanks for everybody. Again, I'm a VCF member. I'm into DEC, maybe Ohio Scientific, and making things. I'm wearing a Make Magazine sweatshirt. But Ted Fried is the guy who did all of the hardware and software design of the emulators I'm talking about. He's in California, works for Apple. He's an embedded hardware engineer and vintage computer enthusiast with a particular interest in the microprocessors that we used in early home computers, et cetera. So these are the places that Ted publishes his projects and how they're going. He has a blog, MicroCore Labs, GitHub repository, everything, the whole design, hardware and software is there. This presentation is going to be on my GitHub, so if you want to go back to it and download the whole thing, you don't have to type in all the URLs. His VCF forum ID is MicroCore Labs, and Ted is pretty responsive on that. All of my communication to Ted has been through the forum. And then also he has a YouTube channel where he kind of shows some of the things running. Final point here is, raise your hand, ask questions. This is a talk. It's interactive. If you want it to be, it's not a kind of a lecture or a core dump. So MicroCore Labs is the collection of Ted Fried's website or internet presence, if you will. He builds plug-in emulators since he's an embedded hardware engineer. He does both field programmable gate array, FPGA type of emulators at the gate level, and also he does ones that are microprocessor based. It's all open source, and you can get to the code and change it any way you want. But this talk is really only about the microprocessor based emulators that he does. FPGA is like another level of hardware engineering that I think the ones that I'm talking about are a little bit more accessible than learning a whole new hardware language and that kind of stuff. So just some definitions up for discussion if you disagree with them. But emulators, when people think of emulators, often they think about pure software emulators that's running on something completely different. But there are also emulators that are hardware-based, like the FPGA ones, or hardware plus software. And they're inside the host vintage computer. So the ones that I'm talking about are plug-in emulators. And cycle accurate has been a lot of discussion. Daniel Benison had one on the 8088, was very interesting. So the way Ted defines it is virtually identical operation and speed is the original CPU. Cycle accurate to a degree, but not cycle exact. So it plugs in, it acts like your CPU. And it replaces the CPU, and they also have an industry term, in-circuit emulation, or ICE. So we don't use that word as a word. So the ones that Ted builds that are microprocessor based, they're all named MCL for MicroCore Labs, or MCL and then 2 letters plus. So the ones that he has there, the MCL 65 plus, that emulates the 6502. There's the MCL 64, and that emulates the Commodore 6510, which are in their products. Still 6502 based, but it's got a different pinout. The MCL Z8 is the Z80 emulator, and the MCL 86 Plus is an 8088, like in the original PC. He also has recently done one for the 68000 called the MCL 68 Plus. So the ones that have asterisks are ones that I personally built and tested in various systems. What does it look like? This is one, the MCL 86 Plus, plugged into an IBM PC. So in the upper right-hand corner, you see a thing with a USB cable plugged into it. There's a circuit board, pins on the bottom to plug into the CPU socket, and then a dev board on the right-hand side that basically does all the work. So what can you do with them, and why are they useful? They can help debug a machine, which I've done, and they can also help you bring up a machine that is missing some things. If you don't have a functioning boot ROM, disk, serial I/O video, you could do that in the emulator, and that'll help you bring up a system that might not otherwise be bootable. You can also emulate part of the system, and that's what essentially it's doing if you're using it for bring up, is emulating something like the memory that maybe isn't working. And Ted always added, also just to have fun. He said, you can do wild stuff like acceleration. Since you've got a faster processor there, it can run literally faster than the one that it replaced, and do like Frankenstein brain swaps that it plugs into the emulator socket, but it's running a different instruction set than was originally designed. And again, you can extend or upgrade a vintage system, maybe even past what they originally developed it for. And we'll talk about some of that stuff later. Any questions as I'm going along? Okay. So the target for a plug-in emulator is, this is a very, very generic CPU diagram. You've got basically in, out, and in and out categories. In is configuration, how does the CPU run? Volts, you've got to get it some power so it can run. Interrupts that it has to respond to. The next one is very important, the system clock. Everything's clocked to a certain time frame. And then command signals that come into the CPU, like wait states and stuff like that. The stuff that goes out, things like read and write commands of when you're pulling data in and out of it, and other command signals. And then the ones that go both ways in and out of the CPU are obviously things like data and memory and peripheral signals. And most vintage CPUs are 40 pins, so that's kind of the footprint that most of it ends up in. So what you need to run an emulator is absolutely something that's faster than the original CPU. Generally, it needs to be way faster than the CPU if you want to do anything with the system while it's in there. You need something that has a lot of memory, hopefully, and RAM to keep all the registers and so on and so forth. and flash to keep the actual emulator program in. And you need enough I/O lines. You've got to have a minimum of 40, obviously, to drive the CPU signals. So the solution to this, or one of the solutions to this, is a thing called the Teensy 4.1 from a company called PJRC. It is a pretty powerful board. You know, the chart would say it's the most powerful in this space, at least for Arduino stuff. And, you know, 32-bit Cortex M7, 600 megahertz, a little bit more than a finished computer runs at. Lots of flash. It's got 8 meg of flash and 1 meg of memory. So that's useful. It also has a bunch of other stuff on it. You saw the USB port. It can also be a USB host if you solder some pins. Total, it has 55 digital I/O pins, but 42 of those are broken out, so you can use that. And all this other stuff I won't read through, but the chart on the lower right kind of gives you a comparison of power. And so the Arduino Mega used to be, you know, like the big monster in the Arduino space, and it's at the bottom, and the Teensy is the tops. So you can kind of see how much more power there is. So the summary is it's a really fast CPU. It actually has onboard overclocking. So by changing a variable, essentially you're changing a PLL, and that is changing how the clock goes on the Teensy. It can go up to 816 megahertz without cooling, and actually even more than that if you're willing to put a fan on it. So it has lots of pins. 42 can be used directly from the pinout here. The software, for me, is kind of the big deal. It's an Arduino-compatible board. You can use the Arduino IDE, and then the emulator is all in C++. So, you know, I said that's an LOL, which means, of course, lots of libraries. As there is in any of the Arduino space, there are lots of libraries. Surprisingly, it's quite affordable, at least I think so. I remember paying $30 for the first Arduinos, and so this is $30 at Amazon or Micro Center.
Can you get really cheap clones of this on like eBay or?
I think there might be some on the Chinese sites, but I haven't tested them, so it's kind of like maybe.
Yeah, you would expect first performance.
Right, yeah, but yeah, $30 is, you know.
It's not that much.
It's not that much. The only thing I'd really say about the Arduino and those kind of products is they are modern processors, and much as we hate it, it is a below 5-volt world nowadays. So it's a 3.3 volt development board, and it's not 5-volt tolerant. So that is, you know, that's just kind of the way the world is. But that's, you know, that's been solved by a couple of things. So what is the, you know, what do the boards look like? You know, I really say the PC board has only, you know, one job, though it's a big one, and that's to safely connect the Teensy pins to the CPU socket. So those are the two major things you see here, the outline of the pins that go into the socket, and on the right is the outline of the Teensy. You know, I have some actual boards here. You're probably too far away to really see them, but this is an image of the 8088 board. There are only 3 chips on this one. On most of them, there are 3 to 5 chips. And those are basically buffers or latches to handle the 3.3 versus 5 volt. Teensy, I said, is a 3.3 volt board, but it will take one 5-volt input, regulate that to power the board, and then there's a 3.3-volt output pin, which can be used to power other things, in this case, the buffer chips. So the logic is you power something with 3.3 volts, and it's never going to go above 3.3 volts because, you know, that's what it does. So this one, surface mount technology, and I know that's kind of scary for some people because it's a new world, but it's really not that difficult to assemble one way or the other. And you know, I'll talk about that a little bit in the build section. The software, you know, it's sort of you think it's complicated, but it's all in one Arduino code file. It's in a .ino. It's all like right there. It's C, C++, and so, you know, if you look at a C code, I always go straight to the bottom of the C code because that's where the main routine is. You know, obviously there's like some setup that it does. There's the classic Arduino thing is, you know, what pins are doing what, their inputs or outputs. You know, there's some of that. And the main loop, you know, is just wild true. You know, get an instruction, decode it, execute it, then do it all over again. It just does that in a loop. So outside of the final page of the code, above that you've got all these routines, all the functions, and those are all the instruction decode, execute functions, et cetera, et cetera. When I first started looking at the code, I did notice some stuff. I started with the 8088, and the 8088 is a, you know, 16/8-bit, and so there are a lot of instructions, but there are also some arrays, and they're used for a number of things. Some of them are ROM images, especially in the IBM PC. You'll see page after page of basically hex code for ROM images, and you can kind of swap those in and out by commenting and uncommenting them. So that can be useful. On the 8088, there was also a hardware debug ROM in the mix. So you know, it's the super ROM or something. So you uncomment that, and it'll boot immediately into a diagnostic. And that can be useful. There are also some arrays that are for pin value lookups, and I'll talk about that on the next slide. But one of the more important concepts is the bus interface. Everything in the emulator goes through a set of routines that talk about where the memory and the I/O is. And that's important because it's basically saying, are we going out to the system for this, or are we keeping it on the Teensy board? And then there's arbitration for what goes where. So you can have some things that you are keeping an eye on, and you said, oh, that's the address for whatever, and instead of letting the system do that, I will emulate that inside the Teensy. Secret sauce for speed. There's some special codes that PJRC has released that are Teensy specific. Fast I/O. If you've ever programmed an Arduino, you may have noticed that the general purpose I/O, GPIO, is slow. Yes. I was going to say very slow, painfully slow. It depends on what you're trying to do. If you're trying to read a button, flash an LED, they're fine. And their focus is on you know, being across a whole platform and being readable and consistent and so forth. But again, you get slow out of that. Teensy allows you to directly access the GPIO. The the code that they do basically transfers into one direct write to a GPI or register, and then the register is, immediately seen on the pins. And, Ted, when I was going back and forth with him on the forum, said, without the fast I/O, none of this would be possible. Meaning that if you tried to use the Arduino libraries, it wouldn't really fly. The next thing is the pin value lookup. Yeah.
But Arduino allows you to do direct access to the registers. It's straight C ignoring Arduino.
Well, yeah, ignoring Arduino.
Yeah. But
Yeah.
you can go right back to it.
Yeah, that's true. But,
It's hardware dependent at that point, though.
Yes.
yeah.
Changing pin directions is regardless of registry.
Yeah, that's another one. So the pin value lookup arrays, I was trying to figure out what they were for. Neither the original CPU nor the Teensy is the pins are not perfectly set up. So there's some routing that is done between the Teensy and the CPU, and sometimes bits are transposed or whatever. It's kind of a scramble. So you can do bit manipulation, ands and ors and shifts and all that other stuff. But that's going to eat up a lot of CPU time. And so what Ted did was he just realized, well, I can just put this in an array, and whatever the value is will come out the other side. So especially in the 8088, he used the pin value lookup arrays to mesh that together. And the array lookups will always be faster than doing binary math. So that's just the way it is. The good news is you only need to worry about those arrays if you're going to change the board layout or actually do a project for a different CPU. Otherwise, you just leave them alone. Just know why they're there. The software, kind of realities are you might have Arduino IDE on your PC or your Mac. You will probably need to upgrade it. I did on every platform that I had. You have to install a utility called Teensy Arduino that actually helps you program the firmware. The IDE for Arduino likes to hold on to menu values that you do, and anytime you open up a new program or whatever, it uses the defaults that you had for the last time, which is not all that helpful. So you have to go in, you have to set the processor speed. So there's a drop down for how fast do you want it to run. You also have to set code optimization. So in the back end, it's GCC compiler, and you can optimize for the size of the code. You can turn it way down, or you can turn it to fastest and faster, fastest. And each of those optimization levels, eats up some memory or eats up some code space. So, all of these use the fastest setting. So to make it a little bit easier to use, I have some forked code from Ted's repository, and in the C code, I set the processor speed and I set the code optimization, so it's a little bit easier to get started. Build information, you got to start somewhere. You got to get a PC board. I grew up etching my own PCBs and stuff like that. Had orange fingers for ferric chloride, and you could still do that, but it doesn't make any sense to do that. You can get very good boards made, cheaply. So you got to get some boards or make them made. Overseas manufacturing is the cheapest, not the fastest way to do it. And JLC PCB and PCB Way are two that I've dealt with. The price per board ends up being quite low, but there's a minimum, so you've got to have 5 or more boards, and the more you buy, the cost per board goes down. So, they're good for that. They're making prototype boards all the time. They're panelizing them, and then splitting up the cost. The flip side is that they are on the other side of the planet, and shipping is high if you want them in any reasonable time frame. Let's say it that way. You can wait a few weeks for a cargo ship to come in, and people that live around Baltimore might not want to do that right now. So I have an eBay shipment coming in from over there, and I wonder where it is and whether it will ever come in.
Maybe it was on that boat.
It might have been on that boat. Who knows? While you're ordering the PCBs, you can also get a solder paste stencil if you like doing the way most surface mount stuff is done in manufacturing. It's not necessary if you want to hand solder it, which is certainly feasible. You can skip the whole hard part of the assembly if you want to, because these two and other ones can assemble the board for you. They have the manufacturing processes to do that. I know that JLC PCB sources their own parts, so they may not be authentic parts, but they will work. And PCBWay sources their parts through DigiKey, Mouser, et cetera. So they can assemble the boards if you want to do that. My main thing on that is if you're going to build just one, it would be best, to try to do a group buy, try to get a bunch of people that want to do it, and spread the cost out. So if you have the components, parts, you can get them from anywhere. You can get them from Mouser, DigiKey, et cetera. I knew I had a lot of boards and eventually would want to put them up, and so I got mine off eBay. I ordered a quantity of the buffer chips. The chips themselves are TSSOP TSOP 20 with a 0.65 millimeter spacing. The only exception of doing this format across the thing is the original one that Ted did, the MCL 65 Plus, is actually dip chips, so that one's very easy. You just remember to get the 3.3 volt chips that are 5 volt tolerant, and that's generally 74HC, 74 VLC, and AHC brand or family. For all the boards, you need to get the headers, 40-pin male-to-male machine pin headers to plug into the socket. Because you may be plugging it in and out. You want those to be pretty sturdy. And then I call them Arduino-like headers. They're long, male-female, 0.01 inch, I think, spacing on those. And just realize that the Teensy is 48 pins, so it's going to be 24 on the side. Don't cut it in half like I had a tendency to do in the beginning, thinking 40 pins. Not the Teensy. Assembling, soldering, the easiest option is to not do it at all and have somebody else solder it for you. So have the PCB people do it. But it's not that hard to hand solder, and I'd actually say if you have not done a surface mount project, this is a pretty good one to start with because they only have a few chips. They're reasonable size. They're not micro miniature. And so you need, a good soldering station, a very, sharp, fine tip for your soldering iron, thin solder, solder wick to do cleanup, and a magnifying glass to just make sure you're hitting the pins right. And again, surface mount is nothing to be scared of, I guess, and they're probably seeing more and more surface mount stuff. So might as well dive in. That's what I did. Pardon? Lots of flux, yes. You can do the drag solder is another way. There are lots of good tutorials on how to do surface mount. Adafruit and SparkFun have some that I know about, and just look it up and try.
There's ways to experiment on Amazon. You can actually buy boards that you can play with.
Right. Yeah. Quick.
Do it right.
Yeah.
It's okay.
Yeah, Quick Chip is a big one in that space. They also have great how to remove surface mount stuff with their solder that's very low temperature. So this is the way I do it, and there are other ways of doing it. Drag soldering is a perfectly good one. What I do is I center the chips on the pads. I tack down pin 1. And then I double check and make sure everything's all parallel and lined up. And then if I need to, I can twist it a little bit to get right on the pad. And then I solder the opposite one, pin 11, on the other side, if I'm counting correctly. Yeah. And then double check the alignment, and then tag down the rest of them. And so I'm not sure if this is an eye test for you folks, but I'm showing the thing, and I just want to do a test on this up or down in terms of the orientation. U3, which direction is it going? Up, okay. U4, which direction is it going? Up, okay. U5, which direction is it going? Down, yes. So the chips, because of the routing, are not all in the same direction, so just be careful with that. Yeah. I have a hot air station that gets a lot of use. Just double check what you're doing, and the chips do not work in the reverse direction is the only thing that I can, kind of say on that. And then, solder the rest of them. Once you've got the two tacked up, you just, drag solder or do the rest of them.
Does the silk screen not give you a hint?
Well,
Why didn't you put a dot on there instead of a line?
not my board. I think this is for machine vision, pick and place. I think that's why they do it this way. Yeah.
Looks like the default keycad footprint, which
That is exactly what it is. Default KeyCAD. And, I'm not an expert in KeyCAD, so yeah. I would have put a dot there. That would be me, but yeah. I was not the machine that was designed for doing that.
a dot or a notch.
Both. Yeah, you can't be too.
Arrow and exclamation point.
Yeah, you can't be too explicit about how you do that. But yeah, he had the KeyCAD up there, and I didn't change it. So anyway, the third option for soldering the surface mount stuff is I call the fancy option. This is the one I've done several times, and that's use a solder stencil. Either an individual one, like the one on the right, and that's from Quick Chip also. That's a 20-pin outline. You tape it up nice to be flat on the board. You apply solder paste to one end of it. You scrape across it with a credit card, and then peel up the solder stencil very carefully. Center the chips on the solder, and preheat the board with a hot plate if you've got one, and then hit it with a hot air station, high heat, low air.
But that won't work with those chips right next to each other.
You mean this
That
one?
particular-
I had to trim it down, honestly. So I should have gotten the solder stencil from them and just do it in one swipe, but I did 4 different swipes on the Z80 boards, and it was longer than hand soldering. So, but it was prettier when it was done.
Drag soldering can be pretty too.
That's true, and I know it's not something that anybody's going to see generally, but there's something about hitting it with the heat gun and seeing the surface tension on the solder move the chips in the right direction with the right spacing. It's just like, wow.
If you get really offline, it moves down one pin.
Well, yeah, that's true, and yeah. And again, the high heat, low air is also a critical session, because I've done some surface mount with the really tiny resistors and stuff like that. And yeah, it's nothing less hardening than taking the component that you're trying to solder to the board and blowing it off the board. Again, don't ask me how I know that. Anyway, so if you like your boards to be pretty, this is the top option, but it's not. And then, soldering the headers on, just make sure they're tight against the board and then parallel to each other and that kind of thing. It's best to have a chip or something like that holding them in place while you're soldering them. Same with the CPU headers. There's some CPU headers that are like a surface mount, like a machine pen socket, but are male. Those are really easy to solder on. Final assembly. So you need to give the Teensy a little surgery. The pin at the upper left hand is the 5-volt in. You'll notice that it shares a pad with the USB connector right to it. So you can power the Teensy board just from the micro USB, or you can, you can power it from the pen when it's in the system. But you don't want to do both. You don't want to use the USB port for your computer to try to power your vintage system from the USB port. Nobody's going to be happy with that. So it's good to have a separation of church and state there. And so you get that done, you cut the pad, then you plug the Teensy into the board and then provide power to the board, and then you're good to go. And also just the alignment, the nice footprint of the Teensy right there, is you'll notice that it has the SD card on the top and the USB port on the bottom. So that's the clue how to plug that thing in. You got to go through the, download the software from the GitHub repository. You can either use Ted's repository, or again, I have a fork of his with just some tweaks to make it easier to get going the first time. Ted has a generic version of the, whatever chip that you're emulating, and I'd say start there with the generic one, because it doesn't do any, acceleration or fancy stuff. So whatever you're plugging it into should just work. You need to install the Teensy Arduino so you can program the thing. Launch the IDE, go into the board manager, select Teensy, select Teensy 4.1, set the speed, set the optimization if you want to do that. You want to use Ted's code. And then, plug the board in a power source, hit verify, compile, goes through the whole process, spits the code, gets ready to spit the code to the Teensy. You have to do something. You have to hit the white button there. But it flashes up a little dialog box that says, okay, hit the button now. You hit the button and it downloads the code, LED blinks, and then it reboots the Teensy, so it's ready to go. So that's the process of flashing the code. I'd quickly like to kind of talk about how I use this to debug a system. I have a Challenger, an Ohio Scientific Challenger 1P. It doesn't have a serial port, and it had a malfunctioning floppy disk. So I could turn it on, I could get into BASIC, but I had this disk drive, so I wanted it to work. So I had already built an MCL 65 plus board because I have a number of 6502 machines, and I tested it on a loaned Apple II. David Guestwine, if you know him, he has a really excellent, he's an OSI guy too. He has an excellent floppy disk program for OSI computers written in assembly called Floppy Test. I know I wanted to use David's code because it allows you to do like an RPM test that's like, is the disk spinning? Is it spinning at the right speed? It'll allow you to move the heads, load stuff, and you can hear it, clunking and so forth on a blank disk. But it's 4.5K, and I did not feel like I could type that in and have something that ran at the end of it. So the process, what I did is David's code was also available as a hex dump. And I took his floppy code, I imported it into Notepad++ and did all the editing to make it look like a C array. I did that. Then I pasted the array into the Arduino code, is just one of the top things. And so it was defined as an array. And I made a small patch to the, small patch to the code, which that loaded the array to 0300, which is the starting address of David's routine. That's the way he wrote it. So then I plugged the MCL 65 Plus into the Challenger. I hit reset, and one of the options on cold reset is to go into the monitor. I did that. And then I typed in 003, 0300 starting address and G for go. And then, then it was, painting on the screen, and then I could move forward. Total time spent on that was about an hour. So that's not too bad. And most of that was just, halfway through it, I said I should have written a program to convert this hex instead of sitting here typing, putting in commas between the stuff. But I test, but this is the array. It's several pages there, but it just looks like a bunch of hex code in an array. That's what all the ROM dumps are inside of Ted's code also. So there's that.
Don't use Notepad.
Don't use Notepad? Okay. Well.
Use an actual editor.
All right.
Well, Notepad++ is kind of an actual.
No, it wasn't Notepad. It was Notepad++. So, but I.
Does it not know what regular expressions are?
Yeah. Kind of. So, anyway, we could talk about editors for a while. But here's the code diff there. At the top is one of the bus interface stuff. Is I'm looking for the address. So if it's coming in and it's saying this is the check to see whether there's a local address, meaning it's local to the Teensy, or it's a system address. So that's the address range, the 0300 to the 15 something end of it. Then return the flag 01, which says that's on the Teensy. Use that memory. The second thing is just defining the counter for the for loop, which is basically when the system's reset, it starts up and it just basically shoves that array into the memory of the Teensy. And from that point on, the code just knows it's there because of the if statement there. So that's all the change that I made to the Arduino code to get the result. And here's kind of the end result. This is the Challenger 1. Yep, naked, lying there. But it is running OS 65D. And in the middle, you can see just above the keyboard is the emulator plugged in there. So after a number of test and retest and going through the hardware and sorting out that disk drive, it got it all running.
The chips or the buffer chips look like through hole.
Yeah, on this one it is through hole. The very first one he did was dip through hole, the 6502. So that one's very low drama in terms of building it. I should have started with that one. So these are kind of blue sky ideas for what you can do with this, because all the code is there. One easy one, because Ted has already written this into his emulators to accelerate your machine. So the emulator running, it has to wait for the next clock cycle. And in fact, most of what it's doing is waiting for the next clock cycle to be in sync with the system. If you take out the extra cycles that it's doing to try to be, cycle accurate, then it's going to run faster because it just doesn't need those extra cycles to do what it did. So there's that. You can accelerate your machine very quickly. You can also use the internal Teensy memory, which is going to be faster than your system. You can write code or port a system test process in C and run it on the Teensy. Ted has already done this for the Commodore 64. It's very system specific. I don't have a Commodore, so I didn't build one of those. But it does a lot of stuff. It does checksums on the ROMs. It checks the PLA. It checks the video memory and does all kinds of stuff. And you can do that kind of thing. You can get a machine to boot, obviously, that is missing some vital hardware, like tape, paper or plastic tape, serial port, video out, keyboard, diskette or hard drive. So there's that. You can easily mirror or increase the system RAM. You can have more RAM than your system ever had because you've got a meg there. Or you can try out different ROM versions, like I said before, using the emulated memory within the system. You can expand a machine using the SD card or use the fast serial over USB. USB port with the Teensy can actually come out as 3 virtual COM ports if you wanted to do that and write to different COM ports for different things. Yes?
So the floppy disk drive you had wasn't working. Did you ever replace that with an SD card as the storage?
I could have, but I really wanted to get my machine working. But yeah, that's an option because the SD card is there. In this instance, somewhat unused. So, yeah, just use the code there. Put a FAT file system on it, and go with that. So that's kind of the expansion stuff you could do. There actually is Ethernet on the Teensy. If you really wanted to get into like networking, there's some pins that you can plug a little RJ45 adapter into it. You can also emulate an extremely rare piece of hardware or something like that. The holy grail of Ohio Scientific is the OSI hard drive. I've been working with Glitch, Jonathan Chapman. He has an OSI hard drive, and we're trying to get it running. But once we completely understand that, I'm not going to find another OSI hard drive. They're just too rare. So what's going to happen with that is I want to emulate the hardware so that I can run the operating systems that it did. You can put in a new or expanded instruction set if you wanted to. So Ted put the Motorola 68000 emulator on the 8088. So we had a 68000 software that he could run on a IBM PC, and that was kind of cool. I don't know how.
And this is why you need custom ROMs.
Right, right. But it could be in the Teensy, so, yeah. You never have to burn an EEPROM again with these things, which is, for me, a big win. And if you want to, I mean, if you want to do something cool like this, all the code's there. An easy putt for me would be the 65816, because it should, you know, possibly fit into the 6502 board. 6800 is missing. 6809. Then, because I'm a DEC guy, I'd like to have the PDP-11 running on it. And the Harris 6120 is the PDP-8 on the chip. So, you know, those are all, you know, kind of cool things that can be done with this. So.
What's the Harris?
The Harris is a chip that DEC worked with Harris to take the PDP-8 instruction set, the 12-bit PDP-8, and put it on a microprocessor. So, you know, that would be something cool. So these are just more links. Again, Ted published his projects all in one big Git repository that was a little bit cumbersome for me. So I did some subtree breakouts of those, of the ones that I've done so far, just as a convenience thing. So that's there. There's some link to the, you know, the headers that you need for it, et cetera, or buy a kit. And then the PJRC downloads. So with that, any more questions? Yeah. Yeah. Yeah, you could do that. You could use it for a COM port. And also Ted's code for the acceleration, you can go in and type codes into that to bump it up and down. And I've thought of, you know, you can write a generic monitor in C that just, you know, does stuff like that. All right. Yep.
Did anybody else have any questions?
Right behind you.
I was looking at the buffers on the board.
Yeah.
And if I'm counting wrong, there were like 26 lines buffered.
Pardon?
Do you know how many lines were actually buffered? Because it didn't look like you had enough buffers to cover 40 pins.
Yeah. I think the output is generally not buffered.
Okay, so you're just
Yeah.
buffering the input pins.
Yeah, so it doesn't actually add up to every single pin being buffered.
Thanks.
So. Yep.
Do you have any for sale?
I had a couple in consignment. I think there's still a couple of Z80 ones that are still out there.
No one sells these boards or something?
No, I asked Ted about that. I said, you know, well, you know, he said he's had several people say they wanted to sell on Teensy, but nobody has so far. I think maybe because they're, you know, they're socket specific, that, you know, they only want to do the 6502 or only want to do the 8088. I may have been the only one in the world who's ever done more than one of those, you know, lines, because I have a bunch of different things. Yeah. Okay. Any other? All right.
Okay, round of applause for Crawford.
All right. Thank you.